All right. So if you go to different sources on the internet or different physics books and stuff like this, you're going to see that people do and talk about Doppler shifts in different ways. Okay. And I think for the most part, they overly complicate the situation. Okay. And so I want to present the way that I think about these things, and hopefully this is going to be straightforward and simple and it'll make perfect sense to you. But all of the equations for Doppler shift involve something like this, where we're saying whatever the observer hears, their frequency, okay, the observed frequency is equal to the source frequency times some ratio. Okay, and the ratio is going to have plus and minuses and V naughts and VS's and or other letters and blah 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 blah. Okay, that's fine. The thing is, though, what does the ratio do? The ratio is either going to increase what is observed. Okay, so if the source frequency is 100, it may cause the observed frequency to go to 110. Or if the observed frequency is 100, all right, it might be different. The ratio could be less than 1, and that causes the heard frequency to be maybe 90. Okay, so it's going to cause that frequency to go up or down. Okay, and we know from experience that if the gap between the observer and the source, all right, is trying to increase for whatever reason, okay? If it's trying to increase or decrease, the gap is increasing, we know the pitch has to go down. On the other hand, if the gap is closing somehow, the distance is getting less between them, then we know the pitch is going to go up, okay? So think about this, what's happening with this particular ratio, okay? So is the ratio going to go up or down? All right, so if the gap is decreasing, this first scenario here, then if the observer is moving, in order to get a larger ratio, a ratio greater than 1, we need to have the numerator increase, or the denominator decrease. Okay, so the numerator could go up or the denominator could go down. Both of those are going to make the ratio get bigger. I'm going to make that a big arrow there. Okay, but when the gap is increased or trying to increase, then we know that the pitch needs to go down. We need a ratio that's less than 1. Now, the way we get the ratio to go down is we decrease the numerator or we increase the denominator, or both. Okay, we could do both like that. Okay, so I'm going to do some examples for you. And I'm going to show you how we put this into work. Okay, so again, we need the ratio to go up or to go down. We've got multiple ways we can get that to happen. So let's suppose, for whatever reason, this guy in a tuxedo is playing his violin and he's hitting a note and it's 440 hertz. Okay. And some dude on a bicycle is going by. Phew. All right. And so what we want to do is we want to say, so the dude on the bicycle, what's he going to hear? Okay. So he is the observer. All right. He is O. And the dude over here in the tux is S. He's our source. Okay. Now, whatever change happens, the information about the source, the observer, always goes in the numerator. Okay. So if it's a source moving, we're adjusting the numerator somehow. Okay. So as he's approaching, all right, what he hears, all right, is going to be the sound that's produced by the source modified by our ratio. Okay, we're always going to have the speed of sound here, that's C, And then in the numerator, I'm going to have 340. Okay, but the question we need to have, okay, is because the equation says plus or minus, which one do we choose? Here's what I'm saying. We need the pitch to go up. We need the ratio to be larger than 1, so we're going to add 10. Okay, and once we do that, we're going to end up with 452.9 hertz. Okay, now it's not a big change, but 10 meters per second is pretty slow compared to the speed of sound. All right, the faster that we made the kid on the bicycle go, the stronger the effect would be. All right, sort of like that. Now, once the kid's on the other side, this scenario at the bottom here, okay, we know that the pitch has to go down, so we need the ratio to drop, to decrease, to be less than 1. Okay, so now in that case, we have the frequency. We still have the 340 on the bottom, but now we're going to go 340 minus 10. Okay, so that gets us a ratio less than 1. That's going to drop our frequency. And once we do that, then we can see our observer is going to hear 427.1. That's a 0.1 there. There we go. Okay, just like that. Okay. Again, okay, so how do you choose plus or minus? You got to think about what's happening with your ratio. Do I need the ratio to go up? Do I need the ratio to go down? Okay, so now let's look at an example. We're going to use the identical numbers, okay? Identical numbers, but now we're going to let the source move, okay? So we got some kind of some kind of ancient ambulance from the Korean War or something. Then we've got an observer out in front and we've got an observer out behind. Okay, so now the period doesn't change because the observer is holding still, but the wavelength is going to be shifted either down or up. Okay, so but we still have the same thing to think about with our ratios. Okay, out front we need the ratio to be greater than 1 because we expect the pitch to go up, but in the back we need the ratio to be less than 1 so the pitch goes down. Okay, let's use the same numbers. Out in front, we're going to have the 440. Okay. Now, when the source is moving, we're going to manipulate the denominator. Okay. So all you really have to keep straight in your head is which one's moving. Okay. If it's the observer, it's the numerator. If it's the source, it's the denominator. Okay, and if you can think of some clever way, how to a rhyme or something to keep those straight, let me know. I can share it with everybody. Okay, so I've got the 340, and I've got the 10, but do I use plus or minus? Okay, now remember, out front, the pitch needs to go up, the ratio needs to be larger, and so we choose minus in there. And when we do that, what we get is 453.3. Okay. Now, on the back side, let's look at the numbers. All right. So we're going to leave the 340 here alone. And then we've got the 340 and we've got the 10. How do we combine them? Well, we need the pitch to go down, which means the ratio needs to be less than 1. So we're going to add those guys together. All right, and that's going to give us 427.4 hertz. Okay, just like that. Now, in the previous problem where we did Shifty Math Part 2, by the way, be careful with that title, right? If you read that too fast. Some of you probably read that too fast and went, wait, what? Okay, back in Part 2, when they were moving towards each other, we found F naught to be 452.9. All right, and when they were moving away from each other, what we found was F naught was equal to 427.1. Okay. Oh, that's a little bit hard to see. I apologize. Hopefully that's okay. The reason I chose the same numbers is because you need to understand that they're not symmetric. Okay, it makes a difference if the source is moving or if the person or the observer is moving. Okay, it makes a difference which is which. We don't get exactly the same answers. Now, if I were more inclined to do a lot of algebra on a Saturday afternoon, I would show you how algebraically that works out. It doesn't matter what numbers you choose to use. You don't quite get the same number. All right, it's always going to be close, but it's not quite the same number. However, I belong to a strict set of Buddhism where we are restricted with how much algebra we can do on a Saturday afternoon. It's weird. I could explain it, but you know, it's in Chinese and it's awkward. Anyway, they're not symmetric, okay? And so we're going to get different answers that way. Okay, let's look at another situation here where both of them are moving. Okay, now I'm going to keep using the same numbers, all right, which is that the speed of sound, I forgot to write them down, is still going to be 340. The velocities are going to be similar or identical, okay, sort of like that. And what I want to do is I want to show you what happens if they are both coming towards each other, okay, or both going away from each other. So we'll do that first. All right, so if they're both moving towards each other, we've got this situation. Okay, so we're going to have the 440. Okay, so let's do the observer part first. All right, if the observer is moving into the sound, the pitch has to go up. We need a larger numerator. 340 plus 10. All right. If the source is moving, okay, we need a higher ratio higher than 1, so the pitch goes up. That means the denominator goes down. So we divide by something smaller. Okay, just like that. So the numerator is bigger and the denominator is smaller. So we get a double effect, and what we get here is 466.7, okay? So it makes quite a difference there. We're getting twice the effect. The wavelength is compressed by the source, plus the period is shorter according to the observer, okay? Boom, 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 boom. All right, now let's look at one where it's away. So now we're going to have the 440. Okay, I'm scrunched for room, so I'm going to not put in my units there. I apologize. Okay, now, so if they're moving away from each other, the observer is moving away, we know the pitch needs to go down, smaller numerator. Okay, but if the source is also moving away, we need a larger denominator to get that ratio to go down. Okay, and that number turns out to be 414. Okay, all right, now there's all kinds of combinations here. Okay, I happen to pick the same numbers for a specific reason. I'll show you in just a second. Okay, but no matter how fast they're going, okay, if they're going towards each other, you know, numerator goes up, denominator goes down. Okay, you could have the bicyclist going away, all right, like this, away from the source, which means we need a smaller numerator, okay? but also have the truck chasing it, which means we need a larger denominator. No, I got that backwards. A smaller denominator. It's tough. You got to think through it carefully. Okay, so you can kind of think what has to happen in each situation. Okay, because the moving source should make the pitch go up, but the fact that the boy's moving away makes it pitch go down. Okay, so you can have these competing numbers like this. All right, so one effect might want to make the pitch go up, the other effect might want to make the pitch go down, and then they're multiplied together. It's fine. It works out just fine. Okay, so lots of different combinations there. Okay. I want to show you, though, what happens if in a situation where the truck, all right, is heading this way. Let's let the boy head this way, and let's keep the same speeds. Okay, let's keep the same speeds and see what happens. So we're still going to have the 440 hertz. Okay, now the boy is moving away. That should stretch out the sound wave. That should make the pitch go up. So if the boy's moving away, the boy's moving away, we need it to go down. It stretches out. The frequency needs to go down. So 340 minus 10. Okay, so that's going to reduce the ratio. Okay, now, but with the ambulance, okay, in order it's moving towards the source, if we're going to make the ratio go up, the denominator must be reduced, which gives us this. Okay, and you can see what happens there. Okay, boop, that cancels itself. All right, and we're left simply with 440. Okay, just like so. Which is good, because if they're both moving, I mean, at the same way, that's kind of like they're both standing still also, right? So that seems to make sense. So the moving sound compresses the waves, but the fact that the source is moving causes the period to be different, and it comes out in the wash to be just fine. Okay. All right, so that's the end of this, and so I'm gonna there's one more part of the videos, okay, that we're gonna go over. Okay, so let me end this here.